Hey everyone, how goes it, and welcome back to Computer Science 146. Today, we're going to introduce a new data structure called heaps. Now, in the last couple of lectures, we've discussed this data structure called a tree. We've also defined what a tree is and what a tree is not. The big thing to keep in mind is a tree does not have cycles. Now let's introduce a new type of tree. This is called a heap, and it is a binary tree structure. However, a heap is not a binary search tree. They do have a lot in common, though. First of all, in a heap, the node's data has to be comparable. Also, a heap has at most two children, a left and a right, which is what makes it a binary tree. The big difference between a binary search tree and a heap is a heap has what's called a heap property. This defines the rules for the heap itself. So for instance, if we had a max heap, this means that the children's value has to be less than or equal to the parent's value. Left and right makes no difference in a heap. It just simply means that in a max heap, you have larger values further up the tree. And we can see that over here in this example. Now conversely, there's another version called a min heap, where children must be greater than or equal to the parent. We'll explore that a little later on. And also, let's just go ahead and assume that the leaf elements are null references. In the last couple of lectures, we introduced trees and implemented them using a linked structure. However, trees can be implemented using an array. Here is an array representation of a max heap. Now this version assumes that the root is at index 0. Now for instance, if we needed to access the left child from a parent, what we do is just take the parent's index, multiply it by 2, and add 1 to it. And you can see this over here. If we were at the root, in other words, if we're at index 0, then 2 times 0 is 0, plus 1 is 1, which is the left child. And similarly, the right child is the parent's index times 2 plus 2. So let's say that we were starting from right here. 2 times 1 is 2, plus 2 is 4. This is how we can index the right child from this index. Now, if we also had to access the parent, what you do is take the child's index, subtract 1, and divide by 2. So looking at this one right here, if we were at this index and we need to access the parent's index, then we subtract 1 from 3, which is 2, and 2 divided by 2 is 1. What may be a little stranger is this one. If we subtract 1 from 4, we get 3. 3 divided by 2 is 1.5, but keep in mind, indices are integers. This causes integer division. And every time there is integer division, you can think of that mathematically as it takes the floor. Or in another way, you can think of the decimal point simply being chopped off. So yes, 3 divided by 2 is 1.5, but that half is completely removed. This means if we start right here and we do 4 minus 1 is 3, 3 divided by 2 is 1. Now, let's go ahead and start the implementation of an array max heap. Now going over here, we've already defined our project and we created our class. Now we want to make this into an abstract data type. So what we need to do is use the generic type T. But just like with a binary search tree, we have to ensure that type T is comparable. In order to do this, we say that T extends comparable also of the same type. Now we're going to go ahead and create the setup for this array-based implementation of a heap. And you'll notice that this is kind of similar to how a stack and a queue was created using an array. So first we start out with a private T array, which we'll just call the heap. Now we're going to create a private int size. And the size is going to be the first null element in our array. This seems very similar to last index that was used before. And finally, as we're going to create a default and a parameterized constructor, it's a good idea to go ahead and establish a default size for your heap. Public static final int default size, and let's just make it 128. With binary tree structures, it's usually a good idea to define the size as some base 2 value. Now we're going to create two constructors, one default, one parameterized. Public max heap. Here's our default. And our parameterized constructor, we're going to allow someone using this max heap to be able to define their own size. Public max heap int size, or int a size. Then, just like before, I'm going to create another method called init to initialize each one of these values. Private void init int a size. Now, as that size is going to define the size of this heap, we need to verify if it is correct. If a size is less than or equal to 0. Now, one way that we can approach this is we can actually recursively call init with this default size and then return from here. And in this way, we can basically reutilize the same method, but this time with a correct and valid size. Now, assuming that that size was correct, now we can construct the heap is equal to typecast t array new object array of a size. And also, we want to set the size property equals to 0, as that is the first null element. We assume that index 0 is the root, so initially the root is null. Now, to connect this with our constructors, the default constructor calls init with the default size. And similarly, this version calls init with a size, and this verifies if that size is correct, and if it's not correct, it recalls it with the default size. But if it is correct, then it just establishes this heap, and we're good to go. However, we did construct this as a new object, which is not quite correct. It was correct for whenever we were using a queue or a stack as an array, but we have to remember that this is a comparable type, which means we need to construct this as a new comparable. In order to make this work, let's see what we could do so far with this. Let's do a heap tester and include the main method. So let's go ahead and create a max heap of some comparable type, and we'll keep it simple by using an integer again. And I'll call this the iHeap equals new max heap of type integer. This is a call to the default constructor. Now, once again, we can construct this heap using a comparable type. But if we were trying to use a type that did not implement comparable, then this would give us a syntax error. Like, for instance, max heap of type object. Object is not assumed to be comparable. Oheap is equal to new max heap of type object. And you can see this gives us a syntax error on this because this type is not comparable. But there are many objects that are comparable. Like, for instance, max heap string. Sheap equals new max heap of type string. Now that we have this, let's figure out how we can add elements to this heap. Adding to a heap is fairly straightforward, but it does work very differently than a binary search tree. Now, when you're adding to a binary search tree, you start from the root. With a heap, you do the opposite. What you want to do is find the first leaf in breadth order. Now, as a reminder, breadth order basically looks at each one of the rows of a tree. And let's assume that breadth order always goes left to right, like this. So what we would do is we try to find the first leaf in this order, which is right here. We add the new element here, and then we have to make sure that we maintain the integrity of the heap. Since this is a max heap, the parent must be greater than or equal to the child. So if we added a new element here that was larger than 9, then we have to do a process called bubbling up. Basically what we do is swapping values that break the heap property. So if a child is greater than a parent, we swap those values until that is no longer true. Let's see an example. Let's add the value 13 to this max heap. So the first thing that we do is scan through in breadth order, and we find the first null element here. We add 13 to there, and now we start that bubble up process. So from that node, in other words, from index 6, we need to access the parent. If we remember how to access the parent, we subtract 1 from that index and then divide it by 2. 6 minus 1 is 5. Divided by 2 is 2, which is why we look at this value. Now 13 is greater than 9. This does not preserve the heap property, so we must swap those values. Now we still can't assume that this is true, because now we have to check the next parent from 13, which is at index 2 now. Once again, 2 minus 1 is 1. 1 divided by 2 in integer division is 0. 13 is also greater than 12, so we must swap those values. Now because we're at the root, we're done. Let's see how we can program this. So first we're going to create public void add TA data. Now, as this is an array implementation of a heap, we know that arrays are not resizable in memory. So if we're adding data to this data structure, we have to worry about if that heap is full. The way that we can tell is by using this size property. This indicates the first null element. If the last element in this array is not null, then the entire heap is full. So if heap at heap.length minus 1 is not equal to null, then we have to return the heap is full. But if that's not the case, we take heap at the index size and assign it to a data. We're just keeping track of this last index, that way we can just simply add this information to it. From there, we have to bubble up. I'm going to separate this into a different method. Private void bubble up. We're going to keep this as simple as possible, and since we're using an array, we don't need recursion in order to reference the parent's values. We can use simple arithmetic in order to access any of the nodes. That's the convenience of random access. So let's go ahead and start. Int index starts at the size. Because if we follow this from here, we know we just added this new element to this index right there before we have bubbled up. Now, while this index is greater than 0, this indicates that we are not at the root, so we would have a parent. And now we have to take the value that is found at the parent and compare it to our current value. So in other words, heap at the index minus 1 divided by 2. This is how we access the parent's value given the child's index. Now we know that the data in this array is comparable, and it is advisable to use the method .compareTo in order to evaluate this. So now we compare the parent to the child, heap at this index. Now compareTo works in the exact same way. So if we discover that this is less than 0, now this indicates that this value was greater than the parent's value. We have to preserve the integrity of the heap. So in this case, we must swap the values. ttemp is equal to heap at the index minus 1 divided by 2. So we store the parent's value. Heap at the index minus 1 divided by 2 is then reassigned to heap at the index. Then heap at this index is reassigned to the temporary value. So now we need to readjust the index is equal to the parent's index, index minus 1 divided by 2. And in this way, it keeps following this value that we just added here all the way up the tree until we're either at the root or a parent is greater than or equal to the child. Now, after we've added the data going back to add, we then call bubble up, and then we increment size plus plus. And that's how you add to a max heap. Now let's take a look at how you would remove values from a heap. The first thing that we have to keep in mind, anytime you remove from a heap, you are always removing from the root. This is very unlike a binary search tree where you can remove any element. A heap must only remove from the root. So the first thing that we do in removal is we store the data that was stored at the root. Then we replace the root data with the data in the last node in breadth order. Then starting from the root, we bubble down the information. And finally, we return the stored value previously at the root. Now going back to bubble down, the way that it works is starting from the parent, you first examine the values of the two children. As this is a max heap, you pick the larger of the two values. Now if that larger value that is found at a child is greater than the value stored at the parent, then much like bubble up, you have to swap. But in this case, you're bubbling down the values. Now we continue this process until the parent's value is larger than any of the children, or we have reached the bound of the tree. Let's see an example of remove. So of course we have to store the value that's found at the root, and that is 12. Now what we have to do is scan through in breadth order, in other words by the rows, until we find the last value. We have to replace the root with this value. So once we know that that is the last value in breadth order, the root becomes that value. Now as we can see, this is no longer a max heap. So now what we must do is bubble down to ensure that we maintain the integrity of the heap. We have to look at the left and the right children. So starting from this index, in other words index 0, 2 times 0 plus 1 is 1. This is the value of the left child. 2 times 0 plus 2, this is the value of the right child. Looking at each one of these, we pick the larger of the two. This means we choose the right child. And as we can see, the value at the right child, 9 is greater than 6. So we must swap those values. Now we're at the bounds of the tree, so we're done. And we can see that this still is a max heap. And finally, we return the value 12. Let's see this one more time. If we were to call remove again, Now we store the return value, which is 9. And again, we find the last node in breadth order. Scanning through this again, we can see that this is the value that we're concerned with. Now, we replace the root value with this value, like that. Then we start to bubble down. Starting from index 0, 2 times 0 plus 1 is 1. So this is our left child, 8. 2 times 0 plus 2 is 2. This is our right child, 6. As this is a max heap, we choose the larger of the two, so we're going to pick this one. As we can see, 8 is greater than 5, so we must swap those values. But unlike last time, we're not quite finished. As you can see, we have a left child, but not a right child. We still need to evaluate those. 2 times 1 plus 1 is index 3, the left child. 2 times 1 plus 2 is 4, which is null, so we don't consider this value. Now we just have to determine, is the left child larger than the parent? And in fact, it is. Now because of this, we have to swap those values. And once again, we've reached the extent of the tree. And finally, we return that value. Let's see what this looks like in code. Public T remove. Now just like remove inside of a stack or a queue, we have to return a value. And also, we only remove from the root. So starting from right here, we're going to store this T ret, the return value, is equal to heap at index 0, the root. Next, we have to replace the root with the last value in breadth order. So if we take heap at index 0, and we know we're maintaining this property called size. This is always keeping track of the first null element. So one behind that null element would be the last element in breadth order. This is why heap at index size minus 1 is the last element in breadth order. Now, just to be doubly sure, we're going to remove the duplicate value inside this heap. So in other words, heap at that size minus 1, we're just going to set that to null. Now what we're going to do is go ahead and decrement that size. We're not going to be using that like we did in bubble up. Bubble down always starts from the root, and we're just going to go ahead and call bubble down from right here, and then also make sure that we return that ret value. Now let's define bubble down. Private void bubble down. Let's go ahead and make sure that we call the method bubble down from our remove method. Now going inside of here, bubble down always starts from the root. So we establish int index is assigned to 0. Now we don't want to go outside the bounds of the tree. And we have that property size that can give us a good indication of where the bounds are. So one of the first things that we're going to look is starting from this index right here, we're going to look first if there is even a left child. So while this index times 2 plus 1 is still less than the size. The size is the first null index, which anything below that index would still be within the bounds of the tree. This indicates that we at least have a left child. Now what we can do is assume that perhaps the left child is the larger of the two children. This is why we assign int big index is equal to index times 2 plus 1. Now if we make an assumption, we have to confirm it. We have to then check if there is a right child, and if there is, was the right child larger than the left? So inside of here, if index times 2 plus 2 That's how we access the right child. If this value is still less than the size, it's within the bounds of the tree. So now we have to check the value of the left child versus the right child. So simply enough, if we take the heap at the index times 2 plus 1, that's the left child, and we compare that to heap at the index times 2 plus 2, the right child, and it turns out that the left child was less than the right child, then we need to reassign the big index to be the right child. Index times 2 plus 2. Now we have determined that we're still within the bounds of the tree, and we have evaluated which of the two children, left or right, were the larger two. Now we must compare that to the parent value that is currently at this index. So, if heap at this index dot compare to the heap at the big index, whether it's left or right, and we determine that the parent was less than the child at this big index, we must swap those values. So, T-temp is equal to heap at this index, the parent value. Heap at the index is now replaced with heap at the big index, whether it was left or right. And finally, heap at the big index is reassigned to temp. Now, if this was not true, we break, because this would indicate the parent value was larger than the child's value. If that's the case, we need to stop this loop. However, if that's not the case, we have to continue down the tree by reassigning this index to the big index. So this is now how we can remove from a heap. I'm going to show two other quick methods before we test this out. Now, just like with stacks and queues, it is a good idea to create an additional method called peek. Remove always removes the first element, while peek observes the first element without removing. So in this case, public t peek. All we're going to do is return the heap at index 0. Another fairly useful method was being able to print out the values that is found inside this data structure. The thing is, we are not going to use a depth-first implementation. In fact, what we're going to do is the breadth-first printout for this tree. Because this is an array implementation of this kind of tree, it's done very simply. Public void print. So all we need is a for loop. For int I is equal to 0, starting from the root. I is less than the size, the first null element, I++. Then from here, all we need to do is system.out.println heap at index I. Now let's see how this works. I'm going to add some elements to this string heap. sheap.add, and let's just add the value a. Something simple like that. sheap.add, let's do AAA. sheap.add AA. sheap.add AAAAA. And I'm just going to add a bunch of A's in here. sheap.add AAAAA. Now, let's sheap.print and see what we have. So would this be correct? In fact, it would be. As this max heap is looking at each one of these strings and comparing them, this string has the most number of characters. So this would be the root. Now, this would be the left child. This would be the right child. This would be the left child of this, and this would be the right child of that. So in fact, our heap does work. Let's see what happens after we remove some elements. sheap.remove. sheap.print. So this was our previous tree, and then starting from here, this is the next largest value, and once again, here's the root, here's the left child of the root, the right child of the root, and then the left child of this value. Heaps are a very powerful data structure, and in future lectures, we're going to explore another type of heap that is used inside of computing and also introduce a brand new sorting algorithm that uses a heap. Until then, I'll see you next time.